We begin with Alison Wendlandt, who's an assistant professor at MIT. She actually did a PhD with Shannon Stahl, who is actually a member of the center now, but apparently, but was not in the early stages of the center when Alison was doing her PhD. She then went to postdoc, I believe, with Eric Jacobson. So a lot of interest in general catalysis. And so in her independent career, she's quickly made a really big name for herself, developing new catalytic transformations. And particularly an interesting program is this one where the CH functionalization is related to selective editing of carbohydrates. So it's a very exciting program. We're delighted to have you as part of the program, Alison, and we're really looking forward to your talk.
Thanks, Hugh. It's a very nice introduction. Let me just share. Let's see. Sorry, 1 second. Hide. Awesome. Okay, thanks again, Hugh, for the introduction. It's always a privilege to have the opportunity to share my group's research, and so I also want to say thank you for the invitation to participate in this event. As Hugh mentioned, my group is first and foremost a selective catalysis group, though many of the methodologies that we've been developing or trying to develop have really been inspired by challenges that we've encountered in carbohydrate synthesis. And so what I thought I might do is sort of indulge myself by sort of taking a few minutes at the beginning of this talk to try to orient you to some of the selectivity challenges that are unique in carbohydrate and glycan synthesis, but which I suspect you'll find similarities within sort of selective catalysis and in particular CH functionalization more broadly. So of course, unlike nucleic acids and polypeptides, proteins, which form these exclusively linear polymers, glycan polymers can exist in this vast array of linear or branched regioisomeric structures. So this has really important consequences for glycan complexity and also diversity, as I sort of highlight here. But also introduces this sort of central, if really very obvious, challenge of site selectivity in glycosylation reactions. So that is, how do you differentiate between multiple nearly chemically identical functional groups within a molecule to, for example, create a glycosidic linkage at the blue, black, green, or red positions shown here. So this slide does not do justice to a lot of the hard work of people who have sort of listed here and sort of trying to identify solutions for site selective glycosylation and otherwise OH bond functionalizations. But suffice it to say, despite many elegant local solutions, in general, I think general solutions to site selectivity are accomplished almost exclusively through the use of protective groups. And so, of course, this is in contrast with, I think, the aesthetic that I was certainly trained in, a sort of CH functionalization aesthetic, which sort of confronts site selectivity head on. And I just highlight for you at the bottom my sort of favorite recent, although it's not that recent, accounts issue on sort of holy grails, where 3 independent groups identified site selectivity as the target of their sort of reviews on potential holy grails in our community and catalysis community. So I'd like to sort of layer on that this sort of second challenge, which is that of diastereoselectivity selectivity. So again, unlike phosphodiester or amide bonds, the construction of a glycosidic linkage, of course, generates a new stereogenic center. So here you could have a new bond formed either from the top or the bottom diastereophase phase here to form either a beta or an alpha glycoside as drawn here. But really, it's not diastereoselectivity that's the problem, but double diastereo differentiation, right? Because both the donor and the acceptor are chiral molecules coming together to create a new stereogenic center. And what we find in carbohydrate chemistry is that indeed the diastereoselectivity of any given glycosylation is influenced not only by the identity of the donor and the acceptor, but also the site selectivity that linkage is being sort of formed through. Again, I'm not crediting anyone. There's a lot of people who work in this area. I'm not crediting anyone with this slide, just sort of highlighting sort of problems. But again, from the aesthetic of someone who is thinking about selective catalysis and in particular diastereoselective catalysis, I have to admit it's it's a little disheartening that some of the most robust methods for creating glycosidic linkages in diastereo purity are not actually diastereo selective at all, but in fact diastereo specific. So here I show an example of ancomeric assistance involving the neighboring protecting group of this sugar, which can robustly generate these 1,2 trans linkages, as I've shown here. So what this, I think, brings us to is the sort of monomers themselves, and I guess I'll sort of suggest that if amino acids are distinguished by their functional groups, then really the language of monosaccharides is to a large extent written in sort of stereochemistry, right? Which is the sort of core monosaccharides differ from one another to a great extent by their relative stereochemistry, right? The 2 epimer of glucose is mannose, the 4 epimer of glucose is galactose, and sort of vice and so on. Although again, there are sort of other sort of functional groups in these monosaccharides. So our group envisioned that the interconversion of sugar diastereomers, is sort of shown here, first might bear sort of a loose analogy, I guess, to the interconversion of functional groups within the context of an amino acid sequence, peptide sequence shown here, or for example, to base editing in nucleic acid synthesis. But might sort of introduce, I guess, an interesting complementary approach to the synthesis of complex glycans. And furthermore, that this kind of stereochemical editing sort of tool might provide an interesting retron for the synthesis of these rare isomers of monosaccharides from simple biomass-derived starting materials like monosaccharides like glucose, galactose, and mannose. And so, of course, we're not the first to think about accessing sugar isomers through isomerization reactions, so semi-synthetic strategies. So this is, in fact, one of the oldest named reactions. You can take glucose, you can treat it to aqueous sodium hydroxide solution, and in fact, you can access all of the stereoisomers and more of glucose. And these reactions involve enolization pathways. So we have a aldose ketose isomerization via enediol intermediate. And so, of course, this is a racemization pathway. And so conspicuous limitation is the formation of unselective and often intractable mixtures through these kinds of chemical means. The solution then is in carbohydrate synthesis has been the use of protecting groups. Here I show a single example where we could start with a protected furanose glucose derivative. We leaving group activation, deprotection, reprotection in the pyranose form, bimolecular substitution with inversion of the stereogenic center followed by deprotection gives the desired C3 epimer. So again, a conspicuous limitation and one that's sort of common to many protecting group-based synthetic strategies is the sort of lengthy and certainly in the case of carbohydrates, bespoke synthetic routes necessary to carry out even sort of simple bond forming and breaking transformations. Enzymes, of course, offer the opportunity to carry out isomerization reactions in not only a selective way, but in the context of completely unprotected monosaccharides. So here I show an example of the so-called isomoring enzymatic isomerization strategy, whereby we can stitch together a sequence of different enzymes in order to convert, again, the same transformation, glucose to its C3 epimer of allose. These enzymes also operate through polar enolization mechanisms, but of course, through sort of enzyme magic, we have we can converge to a single or enriched mixture of products. Here again, the allose is the favored product through this sequence. I'll again highlight a limitation of these strategies because these are enzymatic transformations under equilibrium control. The maximum yield of allose is, of course, dictated by its relative stability compared with glucose, which in this case gives a 2.5% overall yield. So my lab was inspired by these sort of relatively recent and increasing in number reports of radical epimerization reactions in enzymes. So here shown in the biosynthesis of neomycin B from neomycin C. These enzymes utilize the cofactor SAM, and a mechanism is proposed to involve first single electron reduction of the cofactor by 4 iron 4 sulfur cluster to generate this 5' deoxyadenosine radical. This is a potent hydrogen atom abstractor, which removes the H atom from the top face of this sugar. This generates a sugar radical, and then we have redelivery, so a second hydrogen atom transfer step from this pendant cysteine thiol via the opposite diastereophase, which affords the desired product with net inversion of stereochemistry at C5. And so, of course, in the context of the enzyme active site, it's not surprising that we might have explicit regio and also diastereo control in such a transformation. But also, importantly, the enzyme is able to separate this highly reactive hydrogen atom abstractor from a highly potent hydrogen atom donor. So sort of inspired by these pathways, my team set out to see if we could accomplish a similar sort of a transformation, but outside the context of the enzyme, with I think obvious potential pitfalls. Nonetheless, Yang and Hayden took on this challenge. There is some important precedent for selective carbohydrate oxidation that I should share with you. So first, this work by Adrian Menard, which shows that you can achieve a highly regioselective 2-electron oxidation of methyl glucoside by a palladium catalyst. This work was developed additionally by Bob Weymouth, who developed an aerobic variant. And then more recently, Menard has further shown that the same C3 oxidation of this methyl glucoside could be achieved now under photoredox conditions via hydrogen atom abstraction and then sort of trapping with electron deficient alkene. Mark Taylor has developed this work in a very nice way as well, so I'll point you to that reference. So it's sort of building on these precedents, my team was able to identify conditions which actually convert the methyl glucoside into the C3 epimer, the aloside, in nearly quantitative yield. These conditions rely on organic photocatalysts, CCIPN, bulky alkyl thiol, quinupridine, and a benzoate base. In the absence of the photocatalyst, quinupridine thiol, or light, there's no reaction. This is the ideal base, but you can get away with just a sort of commercial touchable ammonium benzoate, though diminished yield and reaction rate. Also, we can replace the CCIPN with the iridium, an iridium-based photocatalyst, although this is about 1,000 times more expensive, and it often leads to undesired side products, for example, over-oxidation. Perhaps most interesting to us was the identification of alkyl thiols as sort of uniquely capable of promoting the desired epimerization. So we assessed a wide array of different potential H-atom donors spanning something like 20 or 25 kcals in bond strength. And really, alkyl thiols were sort of uniquely capable of promoting the chemistry, and I'll touch on that again sort of later on. So using these conditions, we were able to convert biomass-derived monosaccharides, glucose, galactose, mannose, into the four of the five rare sugar hexose epimers, so allose, talose, ultrose, and glucose, sorry. So essentially a single step conversion of biomass into rare sugar monosaccharides. I won't go through much more of the scope, but I wanted to highlight a couple other aspects. So this chemistry works on completely unprotected sugars, although the yield is diminished compared with this sort of C1 protected sugar. Nonetheless, this is 20 times higher yield than we would have obtained using the multi-step enzymatic sequence of unprotected glucose to unprotected allose. And I'll also highlight, since I suspect many of you may not often work with sort of unprotected sugars, I'll highlight that this is not one molecule, but five. And here I show you the purified proton NMR spectrum of this 2-deoxyallose product, where you see the alpha, beta, pyranose, and furanose forms are present in solution. I also highlight this specific example to mention that this kind of epimerization would not be feasible under the polar enolization pathways because of this sort of skipped stereocenter in the C2 position. So we challenged this chemistry with disaccharides and trisaccharides, and these were also successful. This in particular is a favorite example with 16 stereogenic centers, and we find a singly epimerized product as the outcome. C-glycosides, for example, this empagliflozin SGLT2 inhibitor, as well as pyranonucleosides, shown here, are also effective substrates, although now we're starting to stretch the efficiency of the reaction conditions. I'd like to share, in the sort of time remaining, I'd like to share a few of our mechanistic findings for just to sort of support what makes this chemistry feasible. Here I show a reaction under our standard conditions of L-fucose. to this 6-deoxytalose derivative in 70% yield, along with 12% of the recovered fucose starting material. If we isolate the talose product and resubject it to the standard reaction conditions, we obtain only this talose starting material, although in some diminished mass balance, but we detect none of the sort of original starting material, fucose, suggesting that this process is not operating through a simple equilibrium model. One possibility, though, would be that perhaps only the fucose can undergo hydrogen atom abstraction. So only fucose can enter the reaction, and the talose is sort of inert. So suggesting a pathway by which we could sort of self-sort our way from a lower energy species to a sort of higher energy species irreversibly. To assess this, or to test this hypothesis, we looked at a different substrate. So now this methyl glucoside converted again to the allose in almost quantitative yield. We isolate the allose, resubject it to the reaction conditions, but now under deuterium incorporation conditions. So we dewashed the thiol as well as the sugar. And here we isolate nearly all of the methyl aldehyde, but now we see deuterium incorporation into the C3 position. We detect none of the either proteated or deuterated initial starting material glycoside. So what this experiment shows is that indeed both diastereomers react under the standard conditions. So the glucose and the allose are both able to enter into sort of catalysis, but that they converge to a single, we believe, kinetic product. So our preliminary mechanistic model is shown here. We believe this proceeds through two sequential hydrogen atom transfer steps mediated by these two different catalysts. So the first quinacridinium radical cation does a hydrogen atom abstraction to generate this neutral sugar radical, and then thiol redelivers a hydrogen atom and an H atom donation step to afford the stereo-inverted product. I'll show you a few sort of Stern-Volmer fluorescence quenching studies that support this model. So first, using sort of standard conditions, but now using iridium photocatalyst, which allows us to remove the base and simplify the conditions. We see no fluorescence quenching in the presence of adamantane thiol, but some in the presence of quinacridine. This is consistent with a single electron oxidation of the excited state of the photocatalyst, or by the excited state of the photocatalyst of the quinacridine to generate the quinacridine radical cation. In the presence of both quinacridine and adamantane thiol, we really see no change in the steady state fluorescence quenching rate, suggesting that the adamantane thiol is a sort of observer in this process, is not participating. So in the absence of any thiol, we believe that hydrogen atom abstraction can occur, but we never observe any epimer formation. So here I show no thiol, but we've increased the photocatalyst loading, and we detect instead of epimer, the formation of this overoxidized product, this sort of 3-ketone product, which we believe arises from overoxidation of the sugar radical. Further support for the capability of quinacridine radical cation to generate this sort of neutral sugar radical comes from an experiment where we include, instead of thiol, this electron deficient alkene, this vinyl pyridine. And indeed, we do see hydrogen atom abstraction, and we trap to form this new alkylated sugar product in good yield and exceptional DR. Again, no epimer is observed under these conditions in the absence of thiol. So on the basis of this, we propose a hydrogen atom abstraction step mediated by the quinacridine radical cation. And we propose this as an irreversible step, suggesting that the hydrogen atom abstraction step is the regiodetermining step of the transformation. So to try to gain some insight about the role of thiol in this reaction, we ran the same set of fluorescence quenching data, but now using a thiophenol derivative, so this 4-bromothiophenol. Under these conditions, we see no epimerization. So this thiol is not capable of promoting the desired reaction. So again, the thiol itself does not quench the excited state of the photocatalyst. Quinacridine does. But now when we add the thiol and the quinacridine, we see an increased rate of fluorescence quenching. And we have attributed this to the formation, so in acid-base interactions, the formation of a thiolate and a quinacridinium cation. This shuts down oxidation of the quinacridine and turns on, we believe, oxidation of the thiolate to generate the thiol radical. Indeed, independent generation of the thiolate shows a much more rapid fluorescence quenching profile shown here. And so what I think this sort of pseudo square scheme potentially suggests is that perhaps quinupridine radical cation is involved in hydrogen atom abstraction from the thiol to generate the thiol, and perhaps thiol is somehow involved in this chemistry as well. So to test that, we tried to generate thiol radical through through conditions that had been previously reported in the literature, so without the presence of quinupridine in the reaction mixture. So oxidative quenching of thiols, reductive quenching of disulfides, and also thermal sort of initiator-based conditions. And under none of these conditions, which we propose generate the thiol, do we see any epimerization or any reaction at all. So suggesting that hydrogen atom abstraction by the thiol is negligible, and by sort of microscopic reversibility suggests that, again, this hydrogen atom donation step is also irreversible. So here I summarize the sort of key mechanistic findings. We think that both of these steps are essentially irreversible steps. The hydrogen atom donation step is thus the diastereo determining step, and the hydrogen atom abstraction step is regio determining. And so we think that the separation, so first of all, the separation of the two elementary steps is what allows this sort of contra-thermodynamic process to work, but also suggests a clear roadmap forwards for tuning not only the regioselectivity of the hydrogen atom abstraction, but also the diastereo selectivity of the subsequent hydrogen atom delivery step. On the other hand, at this point, so though perhaps we have a roadmap at this point, the site and diastereo selectivities are clearly substrate controlled. And so we're certainly investigating the basis for the selectivity. So why is this reaction so sort of selective? And I don't have a strong answer, but what I can tell you are a few things. First, we think that the site selectivity is not simply related to the strength of the CH bond. So we can calculate the CH bond strengths. So I've conveniently located these numbers by the OH bond, but they're actually the CH bond strengths. And the numbers that we calculate in no way trend with the observed regioselectivities of epimerization from experiment. And so instead, we believe it's factors in the transition state that are responsible for conferring the regioselectivity of the reaction. And in particular, we think the hydricity of the CH bond as it interacts with this very electrophilic quinupridine radical cation, which is doing this H atom abstraction step. So with that, I think I'll conclude. I certainly want to thank my group. It's a special kind of student who joins an assistant professor's lab, and I'm humbled by the hardworking and sort of the talent of these people. Yang really sort of spearheaded this project along with Hayden. Yang has just moved on to a better place, Genentech in the Bay Area, so that's a lucky catch for them. So with that, thank you again for the invitation to speak, and of course I'm delighted to answer or try to answer any questions.
You're muted, Hugh.
I'm surprised that Rios told me I was muted. I think he prefers me to be muted, but that's another story. Anyway, Alison, thanks very much for a great talk. So there's a couple of questions. So one, I'm modifying this question. This is coming from Nick Chiappini from Princeton. So, you know, it's pretty amazing that you can do these reactions on the unprotected sugars. But when you do the reactions, I mean, but unprotected sugars are tough to handle and how to isolate, to chromatograph. And also, as you mentioned, there's more than one structure there. So how do you know that you've got the compound you wanted? How the characterization must be a little tricky.
Yes, yeah, I guess I'll address the non-question and then also the question. So the purification is a nightmare. And although I think we've developed some interesting tools to sort of help us purify these things, in particular, calcium-supported resins, which will interact with the cis-diol containing sugars and not the trans-diol containing sugars, have been super valuable for trying to separate these compounds. Characterization is sort of, I mean, many of these are natural products for the most part, right? So many of these have prior characterization, although it's sometimes, you know, I don't know, a single carbon-13 resonance or something, right? But carbon-13 also has been a really helpful way of distinguishing products. The carbon-13 spectra are very, very different between the epimers, whereas the proton NMR can often be very similar. But yeah, there's nothing special. I mean, it's the normal sorts of characterization tools.
Okay, great. So another question from Kitai Kwan. During the investigation of thiol-based hydrogen atom donor, was there any trend that was observed with different thiols? Thank you for sharing the school carbohydrate functionalization chemistry with us.
Yeah, in general, alkyl thiols, like many alkyl thiols will work. So N-butyl, T-butyl. So it doesn't have to be this like sterically bulky adamantane thiol. That one's nice because it's a solid, so my students prefer working with it because the lab is a slightly nicer environment to be around. It does seem to trend with basicity. So the more sort of basic the alkyl thiol, the sort of better the chemistry tends to do. You know, one of the ways that this this chemistry seems to sort of break down is through protonation of the quinuclidine to quinuclidinium with formation of disulfide. So you essentially somehow, you know, we have a sort of redox imbalance, but the proton from the thiol ends up on the quinuclidine, so this turns off H atom abstraction, and the disulfide ends up, and the thiol ends up as a disulfide by the end of the reaction. And so I think there's also something related to the ability of the thiol or the tendency of the thiol to form the disulfide that also helps the adamantane thiol be sort of most successful among those. So we think that is maybe the sort of like bulkiness trend that sort of underlies that.
And there's a question I'm going to ask because I missed this. We were having a little bit of technical difficulties earlier on. Could you explain why the reaction is so selective for a particular site? You may have said it and I may have missed it, but
yeah, no, we don't know. What I can say is that that's not unique to sort of us, I suppose. So again, Bob Weymouth, Adrian Menard, people who've done some sort of very site selective chemistry on unprotected sugars have also seen very C3 selective oxidation reactions with glucose, for example. So the basis for that is not clear. Again, as I sort of mentioned at the end, we think this is related to the hydricity of the CH bond that sort of seems to predict the regioselectivity of the transformation, but that's not clear at this point.
Okay. And there's an anonymous question, but a good one nonetheless. Could you go in depth on different amines you've used and their site selectivities?
I cannot go in depth. Very few amines work. So Dabco does not work. Substituted quinuclidines don't offer meaningful differences in site selectivities. So the quinuclidine scaffold is a particularly challenging one to try to tune. So of course we have the idea of let's add sort of, you know, the sort of recognition elements into the quinuclidine and see if we can interact with the substrate and get complementary regioselectivities. And so far that has not been, that hasn't conferred major differences. And one reason for that may be that step is quite exothermic. And we think has an early transition state that's supported by carbon 13 KIE data that we have. We have a very small carbon 13 KIE on that sort of C3 position that's undergoing H atom abstraction. So it's probably a very early transition state, which isn't helping the sort of tuning, site selectivity tuning aspect.
Okay, great. And then one final question. This is from Sarah Electia. And she's asking, did you try to deconvolute no reactivity versus formation of undesired stereoisomer for different classes of hydrogen atom transfer catalysts?
I'm not sure I totally understand. Did we try to deconvolute no reactivity from?
Versus formation of undesired stereoisomer.
Undesired stereoisomer. Oh, I see. So you're saying like, does the thiol? Yes. Okay.
Well, to be honest, your guess is as good as mine.
Well, Sarah, I'm going to answer something. What I'm thinking she's sort of saying is maybe, you know, when we look at whether the reaction is successful, we're looking at the conversion of glucose to allose, right? Which is going from an equatorially disposed alcohol to a axially disposed alcohol. So perhaps these thiophenols are effective at, in fact, the opposite diastereoselectivity, which is going from equatorial, axial to equatorial. That we have not assessed. Whether you can essentially run the reaction in the opposite direction using different thiols. But again, so far, that specifically, but so far we haven't seen any actual productive chemistry out of thiophenols.
Okay, excellent, Alison. Well, at this stage, I'd like the audience to join with me and thank Alison for the talk by using Menti. So this is the way we hopefully can respond and show our appreciation.